Hello, this is Team 15, and this is our project on hypersonic dual-mode propulsion systems. Before we can dive deeper into our research, we must first define what hypersonic flight is. This is when Mach is greater than 5, and for our considerations at around 65,000 feet above ground level, it is not easily achieved as there are extremely complicated considerations that we have to make, such as key flight parameters, which in our case would be range and fuel capacity, as well as very strict regulations due to the sonic boom that it creates as the aircraft travels to supersonic speeds. The main questions that we will focus on in this presentation is how many different types of propulsion systems can even achieve hypersonic flight, how many types of propulsion systems are viable for our design requirement and goals, and if or when will we ever get hypersonic flight.
Let's go over some historical examples. The X-43 was an experimental hypersonic drone that achieved a top speed of Mach 9.6. The drone was launched off a rocket that was dropped from a B-52. Once the rocket reached a speed of Mach 7, the drone detached. The X-43 was then accelerated by its single air-breathing scramjet. Next, the SR-71 was a manned supersonic aircraft that was capable of takeoff, landing, and mid-air refueling. This was achieved by a combined turbojet-ramjet propulsion system. Below Mach 1.6, the plane's engine was ducted to act as a turbojet, but after this point, the engine would switch geometries to function as a ramjet, which allowed it to reach speeds of above Mach 3. Our propulsion system will need to combine aspects from both of these aircraft. So here's Kai Wen to talk about our system.
Thank you, Connor. Now I'll be going through the design requirements and assumptions that we set for our analysis. Firstly, our aircraft requires an operating range from subsonic speeds due to FAA regulations to Mach 5 to be considered a hypersonic system. Secondly, our team set the minimum range to be a flight from New York to London to satisfy commercial flight. Next, the target altitude at cruise is set to 25 kilometers above sea level, which is necessary to reduce drag for the hypersonic system to be in operable conditions. Lastly, the systemic requirement for the design would be to be able to support supersonic combustion. We assume that there will be no fuel carrying limit in our calculations. We assume that we'll be at the target altitude for the entire range and ignore any other atmospheric conditions other than altitude in our comparisons. The limitations of our analysis would be that we could not account for the feasibility of manned flight, since all the designs have not been tested for manned flight. Also, due to the novelty of the designs, data on component efficiencies were not available or comparable. Finally, the design we did use to compare were obtained from different conditions, limiting the accuracy of such direct comparison. I'll now pass it on to Arpit for the approach.
We'll be looking at two systems, the hypersonic system and the subsonic to hypersonic attachment system. Within the hypersonic system, there's a large range of operating Mach numbers, and we can optimize combustion efficiency based on these flight Mach numbers. However, there's an absence of turbo machinery, which makes it unable to produce static thrust by itself. Hence, we're looking at the subsonic to hypersonic attachment systems, specifically the turbine-based combined cycle, or the TVCC. These are combined dual-mode ramjet to turbojet systems, which allows like subsonic takeoff. Within the hypersonic system, we're going to compare the dual mode free jet combustor ramjet and the dual combustor ramjet. And then within the turbine-based combined cycle, we're going to be specifically looking at the over-under TVCC and the axisymmetric TVCC. Now going into the analysis.
Okay, I'll be going over the two dual-mode ramjet systems. The dual-mode free jet combustor ramjet consists of one combustion chamber that can operate at both subsonic and supersonic modes. At subsonic mode, the fuel injector operates at the combustor throat, and the flame holders operate along the chamber for continuous combustion. At supersonic mode, the fuel injector operates at the inlet throat, and the flame holders are not required in the chamber due to extreme temperatures of flow that allow automatic ignition of fuel. This single combustion chamber configuration is beneficial to reduce weight and space for more payload and fuel. Furthermore, the presence of free jet during supersonic mode negates boundary layer interactions and localized heating by shockwaves. However, technical challenges may arise due to the complexity of the design. The dual combustor ramjet consists of two combustion chambers, one in subsonic and the other in supersonic mode. There are separate inlets for each combustor. The subsonic combustor that is located before the supersonic combustor runs in fuel-rich condition and acts as a gas generator where fuel is partially burned. This allows for heated fuel-rich mixture to be supplied to the supersonic combustor, increasing stability of the combustion. Furthermore, fuel preparation can be completed within a short line of 3 to 5 feet. The downside of the system is the weight of the split flow inlet and gas generator. Based on the fixed parameters derived from our design requirements and available experimental data, the initial to final mass ratio of both systems were calculated using the range equation. Since the dual-mode free jet combustor has a lower value, we concluded that this system requires less fuel and is hence more fuel efficient.
For the turbine-based combined cycles over-under design, it is made as a turbojet over the dual-mode ramjet with one inlet and a diverter flap to switch between which jet is being used. The shape of the over-under design reduces drag at hypersonic speeds, so it's very useful for sustained flight. However, the system's currently theoretical because the diverter flap is very unsteady when switching between modes. The axisymmetric design has the turbojet in the center of a circular system, with the ramjet being accessed via a bypass flow. The flow rate of the bypass flow can be changed using a variable geometry inlet. Because it has a gradual transition, it's much more steady than the diverter flap system, but its larger frontal area has a much higher flat drag in hypersonic flight regimes, so it's possibly unsustainable.
Combining the analysis from Jia, May, and Winter, we have concluded that the dual-mode free jet combustor ramjet combined with the over-under turbine-based combined cycle is the most optimal. This is due to the reduced drag and the greater fuel efficiency. As our scope and understanding of the design requirements grew, so did our knowledge of hypersonic propulsion and its limitations. The main outstanding problem is a lack of data for the comparison of each propulsion system. We simplified our analysis by directly comparing systems that might not necessarily be directly comparable. The outlook for technology today includes structures and materials for hypersonic flight that are available but have yet to be applied. Many propulsion systems and aircraft are currently in development. To improve our design approach, we will follow a more structured design timeline that would include testing and development to provide a physical deliverable. All in all, our team did well in researching the best hypersonic propulsion system given the available technology and data.